We first stop and see if it has worked.
No, it's okay. Let me proceed. Um, okay, hello everyone. My name is Sylvain Martin, and I'm going to be presenting on behalf of Group 2629. And our final year project is about a low-cost, energy-efficient smart waste management system for binary classification. So over the next few minutes, I'll be taking you through the background, the problem statement, and the solution at hand. So we are seeing in urban waste, Kampala alone generates over 1,500 tons per day of waste, which is improperly managed by use of the manual sorting techniques. So with this, we are seeing that most of this rubbish cannot be properly handled to be separated into recyclable or non-recyclable waste. So with that, we find that most of it is just dumped or littered wherever these disposal units are set up. So with this comes our problem statement. So what we are looking at is that we want to find a solution of where we can separate the waste at the source of disposal. So in that way, we have less of work to do while separating this waste, and we do not have to do the tiresome manual sorting, which is even harder the more the waste goes into its recyclable process. So with that, our solution has what has been established already. So we have IoT bins which mainly use field levels. So this ones just detect if they are full and allow you to dispose in, or if it's full such that it can't allow you to dispose, or if it's empty, allows you to dispose of the rubbish. Then the others, we have those that use deep learning, but these ones are more of industrial-based techniques at larger scales and cannot be usually be implemented at lower levels. Then we have the HAI on microcontrollers. So this is what we have managed to come up with. It's more of a minified version of an AI system that uses computer vision and runs on a small microcontroller, an ESP32, and can easily get uh, uh, to separate the bio from non-bio. And this ESP32 is the one that sends the commands to the respective IoT devices, as my colleagues will be talking about the technicality and how it works. Yes, so we do have a gap where we have high accuracy classifiers. As I said, these ones are more of industrial based. So they use the high vision models to get to and high robotics to get to separate this waste, which is a bit high cost to implement in most of these areas according to the demand of the rubbish and the supply of these technologies creates that gap in that there's a lot of data that there's a lot of waste that needs to be classified or separated, but we have very few machines to do that. So that creates a gap between the two. Then the problem statement in a nutshell. So we're saying that despite of the proven accuracy of the deep learning waste classifiers, there is no low cost or there is no efficient of how we can actually get this to be narrowed down to the point of disposal. So what we are trying to do is that we're trying to scale down the industry level, highly technical machines to run on a smaller microcontroller to achieve the separation of recyclable, bio and non-biodegradable waste at the point of disposal. So with that, I will invite my next colleague to take you through the main objectives.
My name is Nabale Claire, and I'm going to take you through the main objective. So the main objective is to design, develop, and field validate an integrated energy efficient smart waste management system prototype that combines low-cost IoT hardware with a lightweight machine learning for robust binary classification of biodegradable and non-biodegradable waste. So the system integrates image classification, field level monitoring, and remote alerting into a single deployable prototype. So under the specific objectives, we have the 4 steps to a working prototype. The first step was reviewing the existing waste classification and smart bin system to define the requirements. And the second one was collecting and preparing an image dataset for biodegradable and non-biodegradable waste. And one of the datasets we used was the TACO. And the third step is train and quantize a lightweight model that runs on a microcontroller. And that one, we chose the MobileNet V2. And step 4 is building and evaluating the integrated bin for accuracy, cost, and usability. Then about the methodology, it's about the phased build and test approach. And the first phase, we have the requirements, and it involved the phase 1 involved getting the requirements, and those ones involved literature review and selection of components and tools. Then the phase 2 had the data and model, and under the data and model was the dataset collection, training, and quantization on edge impulse. Then the phase 3 is integration that involved hardware assembly with sensors, servers, and GSM model. Then the phase 4 was all about evaluation, testing for accuracy, fuel sensing, cost, and usability. The simulation was done in Wokwi. Then the ML platform was the Edge Impulse. Then our dataset had 300 labeled images. And data collection and model training under methodology, we had the dataset that had 300 labeled images, and with 2 classes, the biodegradable and non-biodegradable, augmented to improve generalization. Then the architecture, when we were before building our architecture, like before building our prototype, we conducted a cooperative model analysis, and we ended up choosing the MobileNet V2, trained as the faster objects, small objects, the FOMO based classifier on edge impulse for a small memory footprint. Then the quantization, the MobileNet V2 was converted to an int8 quantized model, so that it fits and runs entirely on the ESP32CAM. Then the system architecture and hardware, still under methodology, we have the ESP32CAM. This one captures the image, and the HCSR04, it's the ultrasonic field level for detecting the level of the trash in the bin, and PIR sensor detects the approach of the person that wants to use the bin. Then the servo motors actuate the sorting flap and lid. Then the power design, we have the PIR wakes up the camera side that it can work. Then the SIM800L GSM sends field level alerts to the collectors. Am I supposed to explain the results?
Uh, Hello everyone. I'll be taking you through the next slide, a working integrated prototype. So I think I'll start with the next slide. Yeah, so we designed a model that had a validation performance. It achieved 97.9 validation accuracy. The quantized model successfully retained high classification on unseen data with zero cloud dependencies at interference time. Then, as we can see there, we have the test metrics for transfer learning. We're having our area under ROC curve as 0.89, weighted average precision as 0.90, then the weighted average recall as 0.86, and the weighted average F1 score as 0.86 as well. Next, after that, I think we shall be having the confusion metrics. Yeah, we're having the confusion matrix, and as we can see, we have the actual bio at 42 correctly predicted and 6 misclassified as non-bio. Then also we're having 5 misclassified as bio and 39 correctly predicted. Still we're having a precision as that. Then we have a reliable field level sensing and actuation that is done by our sensors. Have a 0.4 centimeters mean absolute error for ultimate distance recordings. Then the PIR sensor, that's the wake up approach. The bin stayed either until motion was conserving power. Then also at the end, we have managed to incorporate SMS alerts are delivered through the GSM notifications. I'll be ending here, calling on to my next colleague. Thank you.
Hello, everyone. Can we proceed to the next slide? So I'm going to take you through the remaining part of the presentation. My name is Sylvia. What the results of this presentation tell us is that on-device classification is feasible because our quantized model held 87.9% accuracy on a microcontroller without any cloud support, which means it is possible for this to run on its own without relying on being hosted somewhere in the cloud. Then balanced precision and recall show that the model does not favor one class, which matters for fair sorting. This means that it is able to detect both the bio and non-biodegradable. Then combining classification with field sensing alerts addresses the gap left by single function smart dustbins. Here where we are combining two methods to address the gap that has not been addressed by the previously implemented ones. Then high usability scores suggest that the design is approachable for everyday and non-technical users, can be used by anyone, not just people who implemented it. Next slide, please. Here we are going to talk about expenditure and how the low cost is more realistic compared to the existing prototypes that have been implemented on a large scale and they are very costly. This means that our product is affordable by design and it is energy efficient, and common modules mean repairs and replacements are easy to use. Yes, we are using simple tools and hardware components that are easy to implement and obtain and to use. Yes, next slide, please. Then the limitations that we faced. Our data set was limited to, okay, what we could access was this data set of 300 images. That limits the variety of materials that the model has seen and can constrain the real world generalization. Then the binary scope, where we are only handling bio and non-biodegradable, is also overclassifying, where if we could be able to expand to more than 2 classes of trash, it would make the model more effective. Then lighting sensitivity, where our camera module is in a darker area where it may not capture the images properly and making classification accuracy drop. Then the insufficient hardware, where incorporation of a highly trained machine learning model onto a limited microcontroller memory capacity limited us in a way that we had a lot to implement, but it had to fit on a microcontroller, which was a limiting factor. Next slide. So a feasible answer to the problem is that the project delivered a working smart dustbin that classifies waste on a microcontroller, which was our main target, with 87.9% accuracy. And it senses field level within 0.4 centimeters and sends remote alerts, all in a limited budget compared to the existing budget. So we achieved low cost, energy efficiency, and accuracy. Next slide. So for our conclusion and future works, we have expanding the data set into a bigger another limitation we had was improving the robustness of the lighting in the camera module with better optics. And another future work was to develop an online dashboard for easy tracking and maintenance between the people who are using the dustbin and the people in charge of collecting. This was, we were trying to implement this in our project, but due to some issues along the way, we were unable to combine the two. So we couldn't merge the dashboard with the project. So that is in our future work. Then adding solar to make it powered without needing to be connected to to like power source or anything, just maybe like solar. Yeah. Then pilot a networked fleet of dustbins with a collection routing dashboard, as I said, that connecting to enable communication and constructing of an advanced mechanism that can handle segregation for more items at the same time, in that if someone drops in a lot of trash, our system can sort it without having to require the person to put in one piece at a time. And that was our presentation. Thank you very much for your time.